Hi guys, so my name is Florence Marie Blanco and
My name is Rachel Ann G. Quero.
My name is Benedict.
I am April Insurias Canyon. I am Richly Comeras.
I am Luis Charles S. Balasa.
I'm Ronaldin Quizon.
And I am Jean Clarence Pitalawi.
Hi everyone, my name is Amar.
I am Walter Jeff D. Samontiza.
I am John Reeve A. Butaya.
And I'm Michael B. Silvestri.
ever wondered why your body heats up when you're running, cycling, or lifting weights? That's because of something called exercise metabolism. It's the engine that powers your workouts, and today we're going to delve into what it is and how it works. Imagine your body as a car. To get that car moving, you need fuel. In the human body, that fuel comes in the form of calories from the food we eat. This is where exercise metabolism comes into play. It's the process of converting those calories into energy to power your muscles during physical activity. There are two main types of exercise metabolism: aerobic and anaerobic. Aerobic metabolism, which means with oxygen, is a slow-burning engine that powers your body during low-intensity activity like jogging or cycling. It uses oxygen to convert carbohydrates, fats, and sometimes proteins into energy. It's like cruising along a country road, enjoying the scenery. On the other hand, anaerobic metabolism, which means without oxygen, is the fast-burning engine that kicks in during high-intensity activities like sprinting or heavy weightlifting. It rapidly converts glucose, a form of sugar, into energy. But because it doesn't use oxygen, it can't sustain this energy production for long. It's like hitting the gas pedal on a racetrack. You will get a quick burst of speed, but you can't keep it up for long. Now, each person's body uses a different mix of aerobic and anaerobic metabolism, depending on the intensity of the exercise, their fitness level, and their diet. For example, a trained marathon runner may rely more heavily on aerobic metabolism, while a weightlifter may rely more on anaerobic metabolism. But what does it all mean for you? Well, understanding exercise metabolism can help you optimize your workouts. For instance, if you're looking to burn fat, you might want to focus on longer, low-intensity workouts that tap into aerobic metabolism. If you're looking to build muscle, you might want to focus on shorter, high-intensity workouts that tap into anaerobic metabolism. To wrap things up, exercise metabolism is the process of converting calories into energy for physical activity. It comes in two forms: aerobic, which is slow burning and uses oxygen, and anaerobic, which is fast burning and doesn't use oxygen. Each person's body uses a different mix of aerobic and anaerobic metabolism, depending on the intensity of the exercise, their fitness level, and their diet.
Hi everyone, my name is Amar. But now, let us first discuss oxygen deficit and steady-state volume oxygen. So, ano nga ba si oxygen deficit? So guys, si oxygen deficit ay refer siya to the delay in oxygen uptake at the onset of exercise. So, ibig sabihin, si oxygen deficit ay tumutukoy sa pagkakadelay sa pagkakaroon ng oxygen sa pagsisimula ng isang exercise. So, ano nga ba ang pwede maging dahilan nito? Ito ay posibleng ang isang tao ay kinukulang ng blood flow sa kanilang lungs, or di naman kaya kinukulang sila ng oxygen sa kanilang lungs. For example, in an hour, an average people or person needs 1.5 liters of oxygen to perform a physical function. If this person inhales 1.0 liters, then the oxygen deficit is 0.5 liters per hour. So next naman, ang steady-state volume oxygen is a plateau in oxygen uptake which is attained within 1 to 4 minutes of constant exercise. So si steady-state volume oxygen ay tumutukoy naman sa oxygen uptake o nakukuha makuha sa loob ng 1 or 4 minuto na patuloy ng pag-exercise. So bakit nga ba ito tumataas? It is because of the gas exchange of response to metabolic acidosis due to lactate accumulation. So next naman natin na pag-uusapan ay ang patungkol sa volume oxygen response of trained versus untrained subject. So sa trained subject will reach steady state faster than untrained subject. So dito guys, ang trained subject is mas mabilis na makakarating sa steady state compared kay untrained subject. So bakit nga ba mas mabilis na makakarating ang trained subject kay untrained subject? It is because si trained subject guys is meron siyang improved aerobic response to stimulus. And ano nga ba si steady state? So, ang steady state guys is the oxygen flow in invariant and equal at each level along the respiratory system. So next naman guys ay oxygen deficit at death or EPOC during light and heavy exercise. So the term oxygen death guys should not be used in exercise psychology. Instead, excess post-exercise oxygen consumption are also known as EPOC. So ano nga ba si EPOC guys? So si EPOC is the amount of oxygen required to restore your body to its normal resting level of metabolic function. So today guys, si EPOC will explain how your body can continue to burn calories long after you finish your workout.
Hi everyone, I am April Servias Canyon and this is my oxygen deficit occurs at the onset of exercise. The workload is greater than aerobic metabolism can support. Takes time to increase aerobic metabolism from the rest to exercise load. The difference between the metabolic need and the aerobic contribution is the oxygen deficit. So also, oxygen deficit refers to the period during start of exercise when oxygen consumption is insufficient to meet that increased energy demands of the body. So this occurs because the body's oxygen consumption initially lags behind the increased energy requirements during the transition from rest to exercise. So as a result, other energy systems such as anaerobic metabolism provide the additional energy needed until the oxygen consumption catches up with demand. For example, oxygen deficit can be observed during high-intensity activities such as sprinting or weightlifting. So, at the onset of the activity, the body rapidly increases and its energy expenditure to meet the demands of the intense exercise. Good day, I am Richly Comeras and I'm
When engaging in different types of exercise, the oxygen deficit and its recovery can be explained as follows. Light exercise. In this case, the body can efficiently meet its oxygen demands during the exercise. As a result, there might be a minimal oxygen deficit which is quickly recovered during the recovery period. Oxygen deficit. A small difference between the oxygen consumed and the oxygen required for the exercise. Steady state. During light exercise, the body maintains a relatively constant oxygen consumption rate, which is close to the resting rate. Rapid portion of the death. Since the oxygen deficit is minimal, the recovery process is also relatively quick. Slow portion of death. As there is a small oxygen deficit, the slow recovery component is not significant. Exercise time and recovery. For light exercise, the time spent exercising and the subsequent recovery period will be shorter, as the body adapts more quickly to the demands placed on it. Heavy exercise refers to intense physical activities that push your body to its limits. In this context, we'll discuss 3 phases of exercise. Deficit. This is the initial stage where your body starts to burn more calories than it consumes.
This can lead to a calorie deficit, which may result in weight loss if sustained over time. Steady state. This is the middle phase where your body adapts to the exercise and the calorie burn remains relatively constant. During this phase, your body becomes more efficient at using energy, and you may experience improvements in cardiovascular fitness and endurance. Rapid portion of depth. This refers to the quick decrease in energy reserves during the initial stages of heavy exercise. As your body uses up its stored energy, it starts to rely more on oxygen and nutrients from your food to keep going. Depth. This term seems to be a repetition of rapid portion of depth and steady state. Slow portion of depth. This could be the latter part of the steady state, where the energy expenditure decreases as your body adapts to the exercise. Exercise time and recovery. The duration of your workout is crucial, as is the same for recovery. During recovery, your body repairs itself, rebuilds muscles, and replenishes energy stores. A proper balance between exercise and recovery is essential for optimal performance and overall health. Factors contributing to excess post-exercise oxygen consumption. Excess post-exercise oxygen consumption, or EPOC, refers to the increased oxygen intake following physical activity. Several factors contribute to this phenomenon. Elevated hormones. During exercise, the body releases hormones like cortisol and growth hormone to help repair and rebuild muscle tissues. This process requires additional oxygen. Post-exercise elevation of heart rate and breathing. After a workout, the heart rate and breathing rate gradually return to normal levels. This process takes time and consumes extra oxygen. Elevated body temperature. Exercise raises body temperature and the body needs to dissipate this heat. Cooling down requires additional oxygen consumption. Restoration of muscle and blood oxygen stores. During exercise, oxygen supply to muscles and blood may be depleted. The body needs to replenish these oxygen levels after the workout. Lactate removal. Exercise can cause the buildup of lactic acid in muscles, which needs to be removed and converted back into glycogen. This process consumes extra oxygen. Resynthesis of phosphocreatine, or PC, in muscles. PC is a molecule that helps provide energy to muscles during intense exercise. After a workout, the body needs to replenish its PC stores, which requires oxygen. The oxygen depth, or excess post-exercise oxygen consumption, or EPOC, is influenced by two primary factors that act relatively quickly. First, resynthesis of phosphocreatine, or PC. PC is a vital energy source for muscles, particularly during high-intensity exercises. The body rapidly replenishes its PC levels within minutes after exercise to restore energy balance, which requires additional oxygen. Number 2, restoration of muscles and blood oxygen stores. During exercise, oxygen supply to muscles and blood may be depleted. The body quickly works to restore this oxygen levels post-workout to maintain normal cellular functions and oxygenated the blood, which also requires extra oxygen consumption.
Hello everyone, I am John Clarence Bitalawi, and this time I'm going to discuss the potential factors contributing to O2 depth low. Oxygen depth, also known as excess post-exercise oxygen consumption, or EPOC, It is the amount of oxygen required to restore the body to its pre-exercise state. And several factors contribute to the accumulation of oxygen depth, and each factors playing a crucial role in the process. Firstly, lactate removal is a potential factor that can lead to an increase in oxygen depth. As lactate builds up in the muscles during intense exercise, it must be removed for proper recovery. Secondly, elevated body temperature can also contribute to oxygen depth. A prolonged increase in the body temperature after exercise may require additional oxygen for cooling and regulation. Furthermore, post-exercise elevation in heart rate and breathing are like contributors to oxygen depth. The body's increased demand for oxygen during this process can lead to a continued need for replenishment. In conclusion, understanding these potential factors contributing to oxygen depth is important or essential for optimizing recovery and performance. So moving on to metabolic response to short-term intense exercise. So during the short-term intense exercise, the body undergoes various metabolic responses to meet the increased energy demand. In the first 0 to 10 seconds of highly intense exercise, ATP production occurs through the ATP-PC system. This system utilizes phosphocreatine to rapidly regenerate ATP for immediate energy use. And this involves the breakdown of carbohydrates and fats in the presence of oxygen to produce a sustained supply of ATP for prolonged energy output. So these metabolic responses demonstrate how the body efficiently adapts to different durations and intensities of exercise to maintain optimal performance.
Good day everyone, I'm Silvestri and going to talk about the VO2 drift. It's the good indicator of your cardiovascular respiratory. The higher the capacity of your VO2 max, the better is your athletic capacity. During your muscles needs and activities like running, your muscles need an adequate supply of oxygen. Your lungs take in oxygen which pump from the heart to your muscles. Metabolic response to exercise. One thing that our muscles typically need is oxygen, but there's something else that our muscles need, and that is fuel. And in this case, muscles fuel is source is ATP, adenosine triphosphate. Lactate threshold is a compound produced in the body during exercise. When you run at the higher intensity for a long period of time, the lactate begins to accumulate in the blood. The point at which your body produces lactate faster than it can clear is called the lactate threshold.
Hello everyone, my name is Rachel Ann G. Carroll.
Incremental exercise and blood lactate concentration. Blood lactate concentration is one of the most often measured parameters during clinical exercise testing as well as during performance testing on athletes. While an elevated may be indicative of ischemia or hypoxemia, it may also be a normal physiological response of exertion. For example, you might choose to run 400 meters around a track at top speed. You then pause for 3 to 5 minutes before repeating several times. This is in part due to the fact that training results in a decrease in lactate production and an increase of lactate reuptake within the body. Potential mechanisms to explain the lactate threshold. Mechanism: the lactate threshold is a point during exhaustive all-out exercise at which lactate builds up in the bloodstream faster than the body can remove it.
The only way to make up the difference is to rev up anaerobic glycolysis, which occurs in environments lacking oxygen. Other mechanisms discussed which probably enhance the lactate threshold but are not considered essential initiators. Low muscle oxygen. As the individual exercises at a higher intensity, oxygen availability in the muscle is insufficient to meet the aerobic system demands. This produces a backlog and pyruvate must be converted to lactate. This is an unlikely scenario as oxygen delivery and utilization is quite efficient potential contributors to the lactate threshold. Oxygen is an important fuel source of our bodies. Body tissues, such as organs and muscles, rely on a stable supply of oxygen in order to work properly. Accelerated glycolysis. As the increasing energy demands of intense work cannot be met by aerobic glycolysis grids alone, glycolysis is accelerated in order to produce a little more energy. Glycolysis, a glucose molecule, is converted into two pyruvate molecules. If the cell cannot catabolize the pyruvate molecules further, it will harvest only two ATP molecules from one molecule of glucose. For example, mature mammalian red blood cells are only capable of glycolysis, which is their sole source of ATP.
Good day everyone, I am Walter Jeff D. Samuntiza, and now first is failure of the hydrogen shuttle to keep pace can increase lactate concentration has been a topic of interest in the field of exercise physiology and sports science for many years. Lactate, often referred to as lactic acid, is a byproduct of anaerobic metabolism that can accumulate in the muscles during intense physical activity. It was previously thought to be a waste product and the cause of muscle fatigue, but recent research has shown that lactate can actually be a useful source of energy for the body. The hydrogen shuttle refers to the mechanism by which lactate is transported from the muscles to the liver, where it can be converted back into glucose through the process of gluconeogenesis. This process allows the body to replenish its glycogen stores and continue to produce energy during prolonged exercise. However, when the hydrogen shuttles fails to keep pace with the production of lactate, levels can accumulate in the muscles, leading to a buildup of lactate in the blood. And this can result in fatigue, muscle soreness, and decreased performance. Historically, the relationship between lactate accumulation and exercise performance has been a topic of controversy and debate. Early research has suggested lactate was a metabolic waste product that caused muscle fatigue and limited endurance. However, in the late 1970s, Dr. George Brooks, a prominent figure in the field of exercise physiology, challenged this belief with his research on the lactate shuttle hypothesis. Brooks proposed that lactate could be used as a fuel source by the body and that its accumulation was not necessarily a bad thing. And then, Brooks' works laid the foundation for a new understanding of lactate metabolism and its role in exercise performance. He demonstrated the lactate produced during intense exercise could be recycled and used as a valuable energy source by the muscles and other tissues. This shift in perspective has had a significant impact on the way athletes train and fuel their bodies for performances.
Hi everyone, my name is John Benedict and I'll be discussing the fuel utilization during exercise can be determined by gas exchange. RER or respiratory exchange ratio is calculated as the quotient of VCO2 or carbon dioxide production divided by VO2 or oxygen consumption. And that is the ratio of CO2 or carbon dioxide produced to O2 or oxygen consumed. CO2 production is an estimate of the relative contribution of glycolysis to energy production. Glucose is broken down through a series of reactions known as glycolysis, resulting in the formation of pyruvate. Pyruvate is further metabolized to acetic acid or acetyl CoA in a process called pyruvate oxidation. During this step, carbon dioxide is released as a byproduct. Acetic acid enters the Krebs cycle, also known as the citric acid cycle or tricarboxylic acid cycle, where it undergoes a series of enzymatic reactions to produce energy in the form of ATP or adenosine triphosphate and reduce electron carriers of NADH and FADH2. NADH is nicotinamide adenine dinucleotide and FADH2 is flavin adenine dinucleotide are both coenzymes involved in cellular respiration, which is the process by which cells convert nutrients into energy in the form of ATP. And ATP is a molecule that serves as the primary energy currency in cells. The electron carriers NADH and FADH2 generated in the Krebs cycle then enter the electron transport chain, where they donate electrons to oxygen to produce water or H2O while generating more ATP through oxidative phosphorylation. So this illustrates the breakdown of glucose to produce energy in the form of ATP, with CO2 being released during both the conversion of pyruvate to acetic acid and the Krebs cycle. If fat enters the Krebs cycle as acetyl CoA, now CO2 is directly produced during the initial steps of fatty acid metabolism. However, CO2 is eventually formed as a byproduct of Krebs cycle as acetyl CoA undergoes a series of reactions to produce ATP and reduce electron carriers NADH and FADH2. So while glycolysis predominantly contributes to CO2 production from the breakdown of glucose, CO2 is also generated during the Krebs cycle regardless of whether the acetyl CoA comes from glucose or fatty acids. This is the percentage of fat and carbohydrate metabolized as determined by a non-protein respiratory exchange ratio or RER. 0.70 RER, 100% fat and 0% carbohydrates. 0.75 RER, 83% fat and 17% carbohydrates. 0.80 RER, 67% fat and 33% carbohydrates. 0.85 RER, 50% fat, 50% carbohydrates, and so on.
Hello guys, I am Luis Charles S. Balasa. And I will discuss the intensity versus fuel source. So, what is intensity versus fuel source? Intensity versus fuel source refers to the relationship between the intensity of physical activity and the primary source of fuel utilized by the body to meet the energy demands of that activity. So, higher intensity workloads. Carbohydrate will become the primary fuel source. So, at higher intensity workloads, the body relies more heavily on carbohydrates as the primary fuel source due to the rapid availability, efficiency in anaerobic metabolism, and the increased demand for energy to sustain intense physical activity. Conversely, at lower workloads, fats will predominate. So, at lower workloads or during less intense activities, the body predominantly relies on fats as the primary fuel source due to their abundance, efficiency in aerobic metabolism, and ability to sustain prolonged energy output without depleting glycogen reserves. So next,
the crossover concept of metabolism versus intensity. So, based sa akong research, the crossover concept of metabolism versus intensity refers to the transition point at which the body shifts its reliance on different fuel source during exercise. It illustrates how the contribution of carbohydrates and fats to energy production changes as exercise intensity increases. So, the crossover concept of metabolism versus intensity illustrates how the body dynamically adjusts its fuel source utilization based on exercise intensity. It highlights the transition from fat metabolism at lower intensities to carbohydrate metabolism at higher intensities, reflecting the body's ability to adapt to varying energy demands during physical activity. So next, what is duration versus fuel source? Duration versus fuel source refers to how the duration of exercise impacts the primary sources of fuel utilized by the body to sustain energy production. The shift in fuel sources during exercise duration is influenced by factors such as exercise intensity, individual fitness level, nutritional status, and training adaptation. For short duration or during the early stages or prolonged exercise, carbohydrates will be the primary fuel source. So, during short duration or the early stages of prolonged exercise, carbohydrates emerge as the primary fuel source due to their immediate availability, efficiency in anaerobic metabolism, reliance on glycogen stores, and ability to maximize performance during high-intensity efforts. For longer duration, fat will become the predominant source. So, during longer duration exercise, fats become the predominant source of fuel due to their abundant energy reserves, efficiency in aerobic metabolism, conservation of glycogen stores, steady energy release, and adaptation to endurance training. This shift towards fat metabolism allows individuals to sustain prolonged endurance activities while maximizing energy efficiency and performance. So next, fuel shifts from CHO to fat during prolonged exercise. So it means during prolonged exercise, there is a noticeable shift in the body's fuel utilization from carbohydrates, CHO to fats. This shift occurs gradually and is influenced by various physiological factors. So the shift from carbohydrate to fat utilization during prolonged exercise is a physiological adaptation that occurs in response to the depletion of glycogen stores, increased fatty acid mobilization, a shift towards aerobic metabolism, conservation of glycogen. That's all. Thank you.
Good afternoon, everyone. I'm Rodelyn Quizon. Sources of fuel during exercise. Carbohydrates are primary source of fuel for the body. They provide the energy needed for both high-intensity and endurance activities. Energy gels and chew are convenient sources of carbohydrates that are often used by endurance athletes. They provide a quick boost of energy and are easily consumed during long workouts or races. Fat, plasma FFA from adipose tissue lipolysis, intramuscular triglycerides fats. Fat is one of the sources of fuel for the body. As low to moderate intensity exercise continues using aerobic metabolism, fatty acid become the predominant fuel source for exercising muscle.
What is fatty acid? Fatty acids are long-chain hydrocarbon molecules that serve as a major source of energy for cells. They can be obtained through the diet or synthesized endogenously. The metabolism of fatty acids involves several interconnected pathways, including fatty acid oxidation, or we can call the beta oxidation, fatty acid synthesis or lipogenesis, and dissynthesis and degradation of complex lipids such as triglycerides and phospholipids.
Fat is one of the sources of fuel for the body. As low to moderate intensity exercise continues using aerobic metabolism. Protein, only a small contribution to total energy production, only 2%. Protein is not considered a major fuel source. However, small amount of amino acid derived from protein can be used as a source of fuel while resting or during physical activity. Blood lactate, gluconeogenesis via the Cori cycle. Blood lactate is not a direct source of fuel for the body. However, it plays an important role in energy metabolism and can indirectly contribute to fuel utilization during exercise. The primary fuel sources for skeletal muscle during exercise are carbohydrates and lipids. Fatty acid, muscle glycogen, which is a stored form of carbohydrates in the muscle, is the quantitatively more important carbohydrates fuel source for the contracting skeletal muscle during exercise.
Hello everyone, I am January A. Butayan. Muscle fuel forces in highly trained endurance athletes. Most likely refers to the ways in which highly trained endurance athletes muscles use fuel like fats and carbohydrates. During exercise, in order to better understand these athletes' performance potential and maximize training and nutrition strategies, this may entail researching metabolic processes, energy production pathways, and the effectiveness of fuel utilization in these athletes. Prolonged in trained endurance athlete describes an exercise situation in which an exceptionally skilled endurance athlete works out for an extended period of time at a workload equivalent to 70% of their maximum oxygen consumption. This suggests that the athlete is working at a moderate intensity, which is probably indicative of a sustained effort over time. As exercise progresses, refers to the changes that occur in the energy systems of the body during continued physical activity.
Into energy for physical activity. It comes in two forms: aerobic, which is slow burning and uses oxygen, and anaerobic, which is fast burning and doesn't use oxygen.
Each person's body uses a different mix of aerobic and anaerobic metabolism, depending on the intensity of the exercise, their fitness level, and their diet.
Understanding how it works can help you optimize your workouts. So the next time you're breaking a sweat, remember, you're not just burning calories.
You're powering a complex metabolistic engine that keeps your body moving.
Hey!